How are the physical properties of matters and non-matters different? Matters, gases, non-matters, heliums, oxygens, mercury, bromine, gold, aluminium, carbon, sulfur. Appears shiny lustrous, the non-gaseous, mostly solids except for mercury. Gases, volatile liquids, are solid. Melting point high, except for sodium, potassium, mercury. Low, except for carbon and silicon. Ductility and malleability. Ductile can be drawn into wire. Malleable can be hammered into different shapes without breaking. Sonorous, make a ringing sound when struck. Brittle if solid. Thermal conductivity good. Pole, accept carbon in the form of graphite and diamond. Electrical conductivity good. Pole, accept carbon in the form of graphite. What are chemical properties of matter? Most matters react with acids, water, and oxygen to give similar products. Chemical reactions of matters with acid. A reactive metal reacts with an acid to form a salt and hydrogen. Metal plus acid is salt plus hydrogen. Examples: magnesium reacts with dilute sulfuric acids to form magnesium sulfate and hydrogen. MgS plus H2 SO4 AQ. MgSO4 AQ plus H2G. Zinc reacts with dilute hydrochloric acid to form zinc chloride and hydrogen. ZnS plus 2HDlAQ. ZnCl2AQ plus H2G. Calcium reacts with dilute nitric acid to form calcium nitrate and hydrogen. CaS plus 2HNO3AQ. 2CaNO3 2AQ plus H2G. With cold water or steam. Some metals react with cold water to form a metal hydroxide and hydrogens. Metal plus water, metal hydroxide plus hydrogen. Some metals do not react with cold water, but will react with steam to form a metal oxide and hydrogen. Metal plus steam, metal oxide plus hydrogen. Magnesium reacts with water to form magnesium hydroxide and hydrogen. MgS plus 2H2O. And then it's MgOH2AQ plus H2G. Zinc reacts with steam to form zinc oxide and hydrogen. ZnS plus H2G to ZnOAQ plus H2G. With oxygen. Some metals react with oxygen to form a metal oxide. Metal plus oxygen, metal oxide. Magnesium burns zinc oxygen to form magnesium oxide. 2MgS plus O2G. 2MgOS. Reaction of zinc with dilute hydrochloric acid. Reactions of magnesium with cold water. Reactions of magnesium with oxygen.
The uses of metals depend on their properties. Every metal has its unique properties. Some metals, such as copper, have good electrical conductivity and are used to make wires. Others, such as gold and silver, are very shiny and are used to make jewelry. Let us take a closer look at the uses of two metals, aluminium and copper. What are the uses of aluminium? Figure 14.5 shows the physical properties of aluminium. High melting point of 660 degrees Celsius. High boiling point of 2467 degrees Celsius. Low density 2.7 grams per cubic decimeter. Good thermal conductivity. Good electrical conductivity. Malleable and ductile. Figure 14.5 Physical properties of aluminium. Pure aluminium reacts with oxygen in the air readily to form a very thin layer of aluminium oxide. This layer prevents aluminium from reacting further with oxygen and water. Aluminium is used to make different objects. Figure 14.6 shows why aluminium is used to make some objects. Aircraft. Aluminium is used in the manufacture of aircraft as it has low density, makes the aircraft light, is strong, does not corrode easily. Overhead electrical cables. Aluminium is used To make overhead electrical cables. Is it? Has low density. Is ductile. Is a good conductor of electricity. Food containers. Aluminium is used to make food containers. As it is malleable. Does not corrode easily. Cans. Aluminium is used make cans. Is it can withstand the pressure inside. Can is malleable. Does not corrode easily. What are the uses of copper? Figure 14.7 shows the properties of copper. Figure 14.7 Physical properties of copper. High melting point of 1084 degrees Celsius. High boiling point of 2567 degrees Celsius. High density 8.92 grams per cubic decimeter. Good thermal conductivity. Good electrical conductivity. Malleable and ductile. Copper is a very unreactive metal and corrodes very slowly. When copper corrodes, a green layer shows some uses of copper is formed on its surface. The green layer prevents copper from being corroded further. Figure 14.8. Uses of copper. Electrical wires. Copper is used to make electrical wires. Is it? Black circle is ductile. Is a good conductor of electricity. Cookware. Copper is used to make cookware. Is it? Black circle is a good conductor of heat. Roofing. Copper is used for roofing. Is it? Black circle is unreactive. Figure 14.8 Different uses of copper. Gold medals are awarded to winners in sporting events. Do you think the gold medals are made of pure gold? The gold medals are usually made of an alloy of gold and silver. What is an alloy? An alloy is a mixture of a metal with other elements. Why are metals often used in the form of alloys? Artificial joints are made of alloys instead of pure metals because alloys are stronger and do not wear away easily. Metals are often used as alloys are more useful. Figure 14.9. To make metals harder, example, and stronger, metals are often used as alloys. To improve, example, the appearance of metals. To lower the melting points of metals, example, to make metals more resistant to corrosion. Brass, an alloy of copper and zinc, is harder and stronger than pure copper or pure zinc. Pewter, an alloy of tin, antimony, and copper, is used to make ornaments because it looks more beautiful than pure tin. Solder, an alloy of tin and lead, has a lower melting point than most metals. It can be used to join electronic parts to circuit boards. Example, cupronickel, an alloy of copper and nickel, is used in coins because it does not corrode easily. Figure 14.9 Why metals are often used as alloys. Table 14.2 shows examples of alloys, their compositions, properties and uses. Table 14.2 Examples of alloys, their compositions, properties and uses. Alloy. Composition. Special properties. Brass. Copper, 70%. Zinc, 30%. Resistant to corrosion. Attractive yellow color. Like gold. Uses. Decorative items, musical instruments, coins. Stainless steel. Iron, 73%. Resistant to corrosion. Chromium, 18%. Nickel, 8%. Cutlery, utensils, medical instruments, pipes in chemical industries. Carbon, 1%. Solder. Tin, 50%. Lead, 50%. Low melting point. Joining metal objects. Pewter. Tin, 956. Antimony, 3.5%. Copper, 1.5%. Bright, shiny color. Like silver. Decorative ornaments. Note, percentages of metals may vary in each alloy. How is the structure of an alloy different from that of a pure metal? Figure 14.10a shows the structure of a pure metal. Figure 14.10b shows the structure of an alloy. What are the differences between the two structures? Metal atoms of the same size. Metal atom. Atom of another element. Atoms of different sizes. Figure 14.10a Structure of a pure metal. Figure 14.10b Structure of an alloy. Why are alloys harder and stronger than pure metals? Figure 14.11 shows what happens to the layers of atoms in a pure metal when a force is applied. Force applied. Metal atoms of the same size. The atoms are packed regularly in layers. The layers of atoms slide over one another easily when a force is applied. Thus, pure metals are soft. Reaction of metals with dilute hydrochloric acid. Many metals react with dilute acids to produce a salt and hydrogen. When a metal reacts with dilute hydrochloric acid, the products are metal chloride and hydrogen gas. The reactions of different metals with dilute hydrochloric acid also indicate how reactive the metals are. A more reactive metal reacts more violently Table 14.4 summarizes the reactions of some metals with dilute hydrochloric acid. Table 14.4 Reactions of some metals with dilute hydrochloric acid. Metal. Observation and equation for reaction. With dilute hydrochloric acid, reacts rapidly to give hydrogen gas. Magnesium. Mgs plus 2HCl Aq. MgCl2 Aq plus H2G. Reacts moderately fast to give hydrogen gas. Zinc. Zns plus 2HCl Aq. ZnCl2 Aq plus H2G. Reacts slowly to give hydrogen gas. Iron. Fe's plus 2HCl Aq. FeCl2 Aq plus H2G. Copper. Silver. No reaction occurs. Gold. Recall the position of hydrogen in the reactivity series. Metals above hydrogen in the reactivity series react with hydrochloric acid to produce hydrogen gas. Based on the reactions of metals with cold water, steam and dilute hydrochloric acid, we can place the metals in order of their reactivity. The reactivity series can be used to predict the behavior of a metal from its position in the reactivity series. Predict the position of an unfamiliar metal in the reactivity series from a given set of experimental results. Worked example 14a. Metal M is above zinc but below magnesium in the reactivity series. Predict the reaction between metal M and dilute hydrochloric acid. Explain your answer. Solution. Metal M will react rapidly with dilute hydrochloric acid to form a metal chloride and hydrogen gas. Order of reactivity: magnesium greater than metal M greater than zinc. Magnesium and zinc react rapidly with dilute hydrochloric acid to form metal chlorides and hydrogen. Thus, metal M will also undergo the same reaction with hydrochloric acid. Apparent unreactivity of aluminium. Aluminium is above zinc in the reactivity series. Why does a strip of aluminium that is left in the open not react with water? We have learnt that aluminium reacts readily with oxygen in the air to form aluminium oxide. This layer is insoluble in water. It prevents aluminium from reacting with water. What is the relationship between the reactivity of metals and their tendency to form ions? In Chapter 4, we learnt that metals tend to lose electrons to form positive ions. The reactivity of a metal is related to its tendency to form positive ions. A more reactive metal has a greater tendency to form positive ions compared to a less reactive metal. For example, when potassium reacts with water, it loses electrons to form positive potassium ions. K's K plus Aq plus E. Magnesium loses electrons less readily compared to potassium. Mg's Mg2 plus Aq plus 2E. This is why magnesium does not react as violently with water compared to potassium. The reactivity series may be used to explain the displacement reactions of metals. Displacement reactions of metals. A more reactive metal can displace a less reactive metal from its salt solution. For example, when iron filings are added to aqueous copper 2 sulfate figure 14.17. Copper metal is precipitated out of the solution as a pink solid when freshly formed, or a red-brown solid. The solution turns green. We say that iron has displaced copper from aqueous copper 2 sulfate. The reaction can be represented by the equation iron plus copper 2 sulfate iron 2 sulfate plus copper. Fe's plus CuSO4 Aq. FeSO4 Aq plus Cus. A more reactive metal forms positive ions more readily. Since iron is more reactive than copper, iron atoms become iron 2 ions and form iron 2 sulfate. The ionic equation is iron atoms become iron 2 ions. Fe's plus Cu2 plus Aq. Fe squared plus Aq plus Cus. Copper 2 ions change to copper atoms.
On the other hand, if a piece of copper foil is dipped into aqueous iron 2 sulfate, no reaction occurs. Copper is less reactive than iron. It has a lower tendency to form ions compared to iron. Thus, it cannot displace iron from its salt solution. Iron filings: blue aqueous, copper 2 sulfate; green aqueous, iron 2 sulfate; red brown, copper metal. Figure 14.17 Iron displaces copper from aqueous copper sulfate. Metal: magnesium sulfate, copper 2, zinc sulfate, iron 2 sulfate, silver nitrate, magnesium, zinc. No change is observed. Solution remains colorless, gray. Deposit of zinc formed on magnesium, pale green. Solution turns colorless, gray. Deposit of iron formed on magnesium, pale green, solution turns colorless, gray. Deposit of iron, formed on zinc, blue solution, turns colorless, red brown. Deposit of copper formed on magnesium, blue solution, turns colorless, red brown. Deposit of copper formed on zinc, solution remains colorless, gray. Deposit of silver, formed on magnesium, solution remains colorless, gray. Deposit of silver, formed on zinc, iron. No change is observed. No change is observed. Copper, silver, blue solution, turns pale green, red brown. Deposit of colorless, solution turns pale green, gray. Deposit of silver, copper formed on iron, formed on iron. No change is observed. No change is observed. No change is observed. Colorless, no change is observed. No change is observed. No change is observed. No change is observed. Solution turns blue, gray. Deposit of silver, formed on copper. From the observations in Table 14.5, we can see that a metal higher up in the reactivity series will displace a metal that is lower in the series from its salt solution. Magnesium is the most reactive, followed by zinc, iron, copper and silver. In a metal displacement reaction, the more reactive metal is oxidized, while the less reactive metal is reduced. Thus, a displacement reaction is a redox reaction. For example, a redox reaction occurs when magnesium displaces copper from a copper to salt solution. The more reactive metal, magnesium, reduces the copper 2 ions to copper. Magnesium itself is oxidized to the magnesium ions. Copper 2 ions are reduced to copper atoms. Mgs plus Cu2 plus Aq. Mg2 plus Aq plus Cus. Magnesium atoms are oxidized to magnesium ions. When an object made of iron is exposed to moist air for some time, a red-brown substance slowly forms on the surface of the metal. This substance is called rust and has the chemical name hydrated iron 2 oxide. Rusting or the corrosion of iron is the process that produces rust. It is the slow oxidation of iron to form hydrated iron 2 oxide rust. The equation for rusting is iron plus oxygen plus water hydrated iron 3 oxide. 4 Fe's plus 30, G plus 2 XHO to 2 Fe, 0, XH2Os. Present in the compound. The X in the chemical formula of hydrated iron 3 oxide indicates the number of water molecules. What causes rusting to occur? The presence of both air, oxygen, and water are necessary for rusting to occur. From the results in Table 14.7, we can conclude that both air and water are needed for rusting to occur. Black circle. The presence of sodium chloride increases the speed of rusting. Besides sodium chloride, acidic substances such as sulfur dioxide and carbon dioxide also speed up the rusting process. Thus, iron objects near the sea and in industrial areas corrode more rapidly because of the presence of salt and other pollutants in the air. How can rusting be prevented? Rust is very brittle and flaky. Thus, when iron corrodes, the rusted surface of iron flakes away. This produces a new metal surface to corrode. Eventually all of the metal will rust and flake away. A lot of money is spent on replacing corroded structures. Thus, it is important to prevent rusting. Rusting can be prevented by barrier methods or sacrificial protection. Barrier methods. The barrier methods prevent rusting by keeping iron and steel away from air and water. Table 14.8 shows some barrier methods. Table 14.8 examples of barrier methods. Painting, oiling, greasing, coating with plastic. This is a common method for large objects such as cars, ships, and bridges. This method is used for machinery, such as tools and machine parts. The protective layer of oil or grease. However, if the paint on the object must be renewed, is scratched, rusting will take place under the painted surface. This method is used for smaller objects such as kitchenware and steel clips. If the plastic layer is torn, the iron starts to rust. Sacrificial protection. Sacrificial protection is the protection of iron and steel against rusting by using a more reactive metal such as zinc. The more reactive metal will react more readily with oxygen and water and Wi. corrode instead of iron or steel. The methods include galvanizing or coating with zinc. Zinc acts as a barrier and keeps iron or steel away from air. Attaching a more reactive metal such as zinc to iron or steel. Table 14.9. Table 14.9 Examples of sacrificial protection. Galvanizing. Attaching a more reactive metal. Zinc. Steel pipe. This method involves dipping the iron object into molten zinc. A thin layer of zinc is coated onto the iron object. The layer of zinc protects the iron or steel object by corroding in place of the iron or steel. This method involves attaching blocks of more reactive metal such as zinc to the iron or steel object. The more reactive metal corrodes in place of the iron or steel. There are two reactions that can occur when metals corrode. Note they are reversible reactions. Iron can lose 3 electrons to form iron 3 ions. Fe 3 plus 3e. Zinc can lose 2 electrons to form zinc ions. Zn 2 plus 2e. Since zinc is more reactive than iron, zinc has a higher tendency to form positive ions. Zinc lose electrons in preference to the iron and prevent iron from forming iron 3 oxide rust. Therefore, more sacrificed to protect the iron or steel. Reactive metals such as magnesium and zinc will corrode instead of iron. As long as magnesium or zinc is present, iron will not rust. This is called sacrificial protection because a more reactive metal is sacrificed to protect the iron or steel. Metals are very useful in our lives. However, only a few metals, the very unreactive ones, such as gold and platinum, occur freely in nature as uncombined metals. Most metals exist in the form of ores. An ore is a compound of the metal, usually the oxides, sulfides. Chlorides are carbonates mixed with large amounts of earth and rock. There are two main methods for extracting metals from their ores: reducing the metal compound ore to the metal using carbon. Black circle electrolysis. The method to extract the metals from their ores is determined by the position of the metal in the reactivity series. The more reactive the metal is, the harder it is to extract the metal from its ore. Figure 14.20 shows the methods used for extracting some common metals. Potassium K, sodium Na, calcium Ca, magnesium Mg, aluminium Az. Extracted by electrolysis. Metals high up in the reactivity series, or reactive, their compounds are very difficult to break down. These metals can only be extracted by electrolysis. Increasing reactivity of metals. Zinc Zn, iron Fe, copper Cu, silver Ag, gold O. Extracted by reduction with carbon. Metals placed in the middle of the reactivity series are less reactive. They can be extracted by reducing their oxides with carbon. Gold is found naturally uncombined. Figure 14.20 Methods of extracting metals based on their reactivity. Recall the position of carbon in the reactivity series. Metals below carbon in the reactivity series can be obtained by reduction with carbon. How is iron extracted from hematite? The main ore of iron is hematite. Hematite contains mainly iron 3 oxide mixed with impurities such as sand and clay. The extraction of iron from hematite is done in a blast furnace. Figure 14.21 on the next page. Hematite, coke, which is mainly carbon, and limestone calcium carbonate are added at the top of the furnace. Blasts of hot air are blown into the base of the furnace. Carbon dioxide is produced. The carbon in coke burns in a blast of hot air to produce carbon dioxide. This reaction produces a lot of heat. Cs plus O2 G less than to CO G. Carbon monoxide is produced. As the carbon dioxide rises up the furnace, it reacts with more coke to form carbon monoxide. Cs plus CO G, right pointing arrow to CO G. Hematite is reduced to iron. The carbon monoxide reduces the iron 3 oxide in hematite to iron. The iron formed is molten and runs to the bottom of the furnace. Fe 0 S plus 3 CO G 2 Fe plus 3 CO2 G. Hot air blast furnace. Figure 14.21 Extracting iron in a blast furnace. Slag impurities are removed. Limestone calcium carbonate is decomposed by heat to produce calcium oxide quicklime and carbon dioxide. Caco S right pointing arrow CaOs plus CO G. Calcium oxide is a basic oxide. It reacts with silicon dioxide, which is acidic, and with other calcium silicate impurities in hematite, to form molten slag. Sows plus CO2 s right pointing arrow Casio 1. Hot waste gases containing carbon monoxide, carbon dioxide and nitrogen escape through the top of the furnace. The molten slag runs to the bottom of the furnace. It floats on top of the molten iron. The slag and iron are tapped off separately. Slag that floats on top of the iron prevents iron from being oxidized by the blast of air. Slag is used as a material to make roads and is often added to concrete to build houses and other structures. The iron extracted from blast furnace will be further purified. Carbon and other elements such as nickel and chromium are then added to the pure iron to make different types of steel. How is aluminium extracted from bauxite? Aluminium is extracted from its ore, bauxite, by electrolysis. The main ore of aluminium is bauxite. Bauxite contains aluminium oxide mixed with impurities such as iron oxide and sand. Aluminium is between magnesium and carbon in the reactivity series. The extraction of aluminium from its ore, bauxite, takes place in two stages. Aluminium oxide is obtained from bauxite. Sodium hydroxide is added to bauxite to dissolve aluminium oxide and separate it from insoluble metal oxides. Pure aluminium oxide, alumina, is obtained. Pure aluminium is obtained through electrolysis. In order for electrolysis to take place, the aluminium oxide must be molten. Aluminium oxide has a very high melting point, over 2000 degrees Celsius. It is difficult and expensive to keep aluminium oxide in the molten state. It must be dissolved in molten cryolite, a compound of aluminium. Cryolite lowers the melting point of aluminium oxide to save energy and costs. Electrolysis is carried out in a large steel tank, figure 14.22. The tank is lined with carbon, graphite, acts as the cathode. Blocks of carbon are hung in the middle of the tank, acts as the anode. At the anode, the oxide ions 0 undergo oxidation at the anode to form oxygen gas. 20(0) plus 4e. At the cathode, the aluminium ions Alt undergo reduction at the cathode. IHE oxygen gas then reacts with the anode to form carbon dioxide. Greater than AI, A plus 3E. Cs plus 0, G greater than Colorado, G. Due to the reaction with oxygen, the carbon anodes need to be replaced regularly. Molten aluminium sinks to the bottom of the tank and is removed periodically. Summary. The overall reaction is steel, tank, right pointing arrow, 4AI, plus 30, G, 2Al, 0, carbon plus, anode, plus, carbon, cathode, molten cryolite, and aluminium oxide, molten, aluminium,